Now in this lecture we are going to implement Dijkstra's algorithm in Java. So as we mentioned before, in case of breadth first search algorithm, we are finding shortest path problem in unweighted graph. So here in case of Dijkstra's algorithm, we have to create weighted graph and then we have to implement Dijkstra's algorithm. So that's why the first thing that I'm going to do, I'm going to create weighted graph. Now to create a weighted graph, first thing we should do, we should create weighted node. So first thing I'm going to do over here is I'm going to create weighted node over here as a file. Then I'm going to create weighted node class inside this file over here. Now here first I'm going to import Java utility file library because we are going to use data structures from this library. Then I'm going to declare our class like this: public class weighted node. Then here I'm going to declare the properties of node one by one. Now the first property will be the name of node. So it's going to be public string name. Then I'm going to declare array list in which we will have neighbors of this node over here. So it's going to be like this: public array list. So it's obvious that it's going to be the type of weighted node. So we are just going to copy weighted node from here and pass it over here. And we are going to name it neighbors, because in this case we are going to save neighbors of weighted node to these neighbors array list over here. So I'm going to declare it like this. Then the next property that we are going to create, we are going to create hash map. So we are going to use hash map in which we are going to save the weight of edge. So here we are going to have a node and integer in which we are going to save the weight of map. So it's going to be like this: public hash map. As a key is going to take weighted node, and as a value we are going to have integer in which we are going to save the weight of node. So it's going to be like this, in which we are going to save the cost of node. So it's going to be weight map is equal to new hash map. Now then the next thing that we are going to do, we are going to declare is visited property, then parent property, then distance property, then index property. So it's going to be like this: public boolean. So with this we can identify that if this node is visited or not. So by default it will be set to false. So the next property is parent of the weighted node. So it's obvious that the parent of weighted node will be the weighted node. So I'm going to name it parent. Then the next property is the distance. So we are going to make it distance like this. And then the next property is index. So it's going to be index. Then inside constructor we are going to initialize the name of the weighted node. And we are going to set the distance to the infinity. In this case, it's going to be integer.maximum value. And we are going to set the index of weighted node that we get from the parameter. So our constructor for this class will be like this: public weighted node. So it's going to take two parameters, string name and integer index. And this name will equal to name and distance will equal to integer.max value. So this means that we are setting the distances to infinity, and index will take the value that comes from this parameter over here, index. So with this we can identify the index of node. Now with this we have successfully implemented our weighted node over here. Now here I'm just going to create two extra methods which overrides the standard methods of this class. So in this case we are going to override toString method, in which whenever we are printing weighted node to the console, in this case it's going to print out the name. So I'm just going to put it like this: add override. So it's going to be public string to string. So it's going to return the name of the node. Now here when we are going to implement the Dijkstra's algorithm, we are going to use priority queue. So when we are using priority queue, we need to be able to compare these nodes over here. So to make these nodes comparable, I'm just going to implement comparable for this weighted node over here. So it's going to be like this: implements comparable weighted node. Then whenever we are implementing comparable, we need to override compare to method also. So I'm just going to put it over here like this. So override is going to be public int compare to. So as a parameter it's going to take weighted node O, then it's going to return this distance minus O dot distance. So with this we are making our weighted node class comparable because we are going to use priority queue. So with this we have successfully implemented our weighted node class. So basically what we are doing over here is we have implemented all properties of weighted node inside this class over here. Now the next thing that I'm going to do, I'm going to create weighted graph itself. So for weighted graph, we are going to create separate class. So it's going to be like this. So inside this file, the first thing that we are going to do, we are going to import over here Java util library, because we are going to use priority queue and array list from this library over here. So then we are going to declare our class like this: public class weighted graph. So inside this class, the first thing that we are going to do, we are going to create node list in which we are going to have the nodes of graph. So it's going to be created by using array list as we did before. So it's obvious that array list will be the type of weighted node. So I'm just going to copy and paste it over here, and I'm going to name it node list. So it's going to be new array list with the weighted node. Now in this node list, we are going to save our nodes that we have in our graph. Now then, the next thing that we are going to do, we are going to create constructor for this weighted graph over here. So it's going to be like this: public weighted graph. So inside constructor, the parameter that is going to take is going to take the parameter of node list, because whenever we are creating weighted graph, we are creating node list, then we are, based on that node list, we are going to create graph over here. So it's going to be node list is equal to this node list that we are getting from the parameter. Now with this, we have successfully implemented our weighted graph. Now after implementation of weighted graph, the next thing that we are going to do, we are going to implement our Dijkstra's algorithm. So in our previous lecture, we have discussed the pseudocode of Dijkstra's algorithm. So here I'm going to implement that pseudocode in practice. So I'm going to declare our algorithm like this. So the name of algorithm will be Dijkstra, and as a parameter, it's going to take source node. So the source node's type will be the weighted node. So I'm just going to put weighted node, and the parameter will be node. Now here, the first thing that we are going to do, we are going to create priority queue. Then I'm going to set the distance of the node that we are getting from the parameter to 0, and this will make sure that we start from this vertex in priority queue as the distance is minimum, because all other distances are set to infinity. So I'm going to declare it the priority queue like this. So it's obvious that it's going to be the type of weighted node. So I'm going to name it queue and new. So let me just copy it from here. New priority queue. Now then, the next thing that we are going to do, we are going to set this node's distance to 0, because we are going to start from this node in priority queue. So I'm going to set distance of this node to 0. Now after doing so, we are going to add all nodes that we have in this node list over here to this priority queue. So I'm going to call add all method of the queue. So it's going to be add all, and as a parameter, I'm going to pass node list. Then inside loop, we are going to check that if queue is not empty, we are going to dequeue the element from the priority queue, and we are going to check neighbors of that node, and based on the distances, we are going to update the distance of neighbors, and we are going to set the parent of neighbors to the present node. So it's going to be like this: while priority queue is not empty, then in this case we are going to dequeue the element. So this element will be the type of the weighted node. So that's why I'm just going to create a new variable over here with the type of weighted node. So it's going to be current node, and in which we are going to save queue remove. Then we are going to look the neighbors of this current node over here. We are going to check that if neighbor is not visited, and if the known distance of neighbor is greater than the new path, then we are going to update the distance of neighbor. So it's going to be like this: for weighted node neighbor in current node dot neighbors, we are going to check that if the neighbor is not visited. So this means that if the neighbor is inside this queue, it means that we have not visited it. So if we have visited it, it should come out from the queue. So that's why I'm just going to use the contain method of the queue. If the neighbor contains in this queue over here, it means that we have not visited it. So I'm just going to put it over here like this. Then I'm going to check that if the neighbor's distance is greater than the new distance that we are calculating, in this case, we are going to update the neighbor's distance. So it's going to be like this: if neighbor.distance is greater than the current node's distance plus the cost of the edge that comes from this current node to the neighbor, in this case, we are going to update the neighbor's distance. So it's going to be like this: current node dot distance plus, we are going to use the hash map that we created in our weighted class. So in this case, we can get the cost of the edge. So it's going to be like this: plus current node dot weight map. So let me just copy it from here. Dot get. So we are going to use neighbor. So this is calculating the cost of edge that comes to this neighbor over here. In this case, it means that we have to update the neighbor's distance. So I'm just going to copy it from here and paste it over here, and it's going to equal to this cost over here. So the new cost will be the less than its cost, because initially the cost of neighbor will be infinity. So if we update it to this cost over here, we are getting the new cost. Then we are going to update the neighbor's parent to the current node. So it's going to be like this. Now after doing so, we have to refresh the priority queue. So to refresh the priority queue, we are just going to remove the neighbor and add the neighbor again. So with this, we are going to refresh the priority queue. So it's going to be like this: queue.remove neighbor and queue.add neighbor. So with this, we are refreshing our priority queue over here. Now with this, we have almost done with our Dijkstra's algorithm, but at the end, we are going to print a table of node with the minimum distance and shortest path from the source. So I'm going to put a new loop over here in which we are going to see the shortest path in the console. So I'm going to put for loop like this: for weighted graph. So for weighted node to check, inside node list, we are going to print out something like this: system out.print. So it's going to be like this: node. So I'm going to put node to check and plus distance. So it's going to be concatenated by the node to check node distance, and we are going to put path over here. So it's going to be path like this. Now after putting path over here, we have to print out the path to the console. So as you remember, in our previous lectures, we have created path print function. So I'm just going to put the name of function over here, and I'm just going to copy the code that we created in our previous lecture to this class over here. Now at the end, we are just going to put system out print. Now with this, we have successfully implemented our Dijkstra's algorithm over here. Basically, what we are doing over here is we are enqueuing all elements to the priority queue, and we are setting the initial instance to 0. Then based on this instance, we are calculating the new cost of each node. If the new cost is less than the cost that we have in our node, then we are updating the cost of that node. Otherwise, we are continuing to the other nodes over here. Now with this, we have successfully implemented our Dijkstra's algorithm. Now let's see how this is working in practice.